All right, let's do it. Is this as zoomed in as it could be? Could be more. There we go. So I want to talk about chapter 11. It's a fun chapter. We're finally getting to apply all the things that we've been talking about. Like we learned about like how to make pretty graphs. We learned how to do simulations. We learned how to talk about probabilities. Like now it's finally time to like bring it all together, which is really powerful and cool. So that is what chapter 11 is about. We're going to learn how to make some ask some questions. Sorry, didn't realize that wasn't down yet. We'll learn how to ask some questions about data and how to answer them. We're going to test some hypotheses that we come up with. It's going to be great. So this is chapter 11 stuff. Please start reading that one. And yeah, I don't have a ton of slides to show you today. It's just going to be mostly examples, and they will be fun. So here is a fun word. So this is a term you may have heard of because of the rise of AI everywhere, but have we heard the word model before? Like machine learning model? Like that's a thing. So a model, all that is, if you've heard of it, that's cool. But if you haven't, that's fine too. A model, all it is just a kind of like a black box that's trying to describe your data. You're trying to learn a model that like understands your data in a certain way. So it's a set of assumptions you can say about the data. It's like you can use it for prediction, for example, or you can use it to like describe things. Okay, so that's very vague. I know. We'll give you some examples though. So yeah, when we are in data science, which is just a buzzword, right? So machine learning, data science, they're very, very related. A lot of our models are going to have some assumptions about randomness. It's like that's very easy for us to simulate things if we're trying to describe a process. We're assuming it's happening due to randomness, and that's called a chance model. You'll hear that phrase strewn about in your textbook. And yeah, so like you can think of the model as a black box, more or less. Just like this is my data, or this is my set of assumptions about the data. Does it fit my model? Or sorry, does my data fit my model? Like this is, I'm feeding in ideas and extracting things as well. Like that's our description of some process, completely random sometimes. But yeah, our goal is that if we can simulate, if we can make a simulation with a chance model, according to our assumptions, we can we know how our model was defined, and so we can make some predictions from it. And so what we'll do is we'll try to make some predictions with our model based on randomness. I know this is very vague right now. And that leads to some simulations that we can program. And then we'll compare that to the data that we actually saw in our data set and see how closely our model predicted things. So that's the goal. Like we have a question, we think that the world works like this, we'll come up with a model to do that kind of prediction, and we'll feed ideas in and get ideas out, and we'll see how closely it modeled the real world. That's kind of why it's called a model, I guess. So yeah, we're going to make a randomness simulation-based programming way or programming idea of something, and we're going to see how well that random programming idea is fitting our data that we see in real life. Like, was that the real reason? Like, was that the true cause, this random idea for why we saw that data? Okay, so yeah, if the data and the predictions are not consistent, they're not the same, that means your model is not describing the real world properly enough, and so you'll have to try a different model. But yeah, a model is just your set of assumptions about the data. You think that those are the correct assumptions that are driving the reason you saw that data. Okay, so that is all incredibly vague. Here is a very nice and concrete example from your textbook. So it's called, oh wait, did I forget to do attendance, by the way? Sorry about that. Getting ahead of myself. Let's do attendance. My bad. It's been a long week already. Let's, yeah, excuse me. And let's go back to this. So the idea, our model is a set of assumptions about the data. If we make a model and we describe it in terms of random processes, we can program it and we can see how well it matched the data that we saw. So here is a good example from your textbook. It is not a great story, honestly. If you look it up on Wikipedia, it's worse than even what your book has said. But back in the day, when they were doing jury duty, they'd never called in women, first of all, which is a problem. And then also there was a bit of racial bias as well, especially in the South. And so here's an unfortunate story. So there was a man named Robert Swain, and he was black, and he was convicted in the South, in Alabama, for a crime. And his jury was entirely made up of white people, even though the population of the county in which he was arrested was probably not entirely 100% white, of course. So that is an issue. And so he appealed that conviction because he was like, I want a jury of my peers. You did not give me a representative jury. This doesn't seem right. Black people were systematically excluded from juries in this county in Alabama. Okay, and so that was his argument. Made it to the Supreme Court, and it was unfortunately struck down, which is quite sad because we were going to prove that there really was racial bias on that jury, and it's quite unfortunate. Here's the ruling from the Supreme Court, by the way, if you want to read that. It is not fun. It's a sad case, but the Supreme Court ruled that a defendant is not constitutionally entitled to a proportionate number of his race on the trial jury or the jury panel, which is not the best ruling, in my opinion. But that's what happened, and we can prove, though, that he did not get a representative jury. It was a sad thing, and it happened. And here's the numbers that they used in the Supreme Court case. So 26% of eligible jurors in that county in Alabama, like the people who could get sent out a message saying come to jury duty, there 26% of the population of the county that was above 18 and American citizens able to go to jury duty. It was 26% of the population. All right, 26% of the eligible jurors were black, but only 8% of the panel of the people they were choosing from. I don't know if you guys have ever been to jury duty. Hopefully, you have not had to go for too many times yet in your life. But the idea is they bring you into a room, right, and they pick a starting jury, and there's a bunch of backups in the back, and that's the eligible panel that you could be chosen from. And they make the jury out of that. So the only 8% of the panel, 100 people that would have eventually turned into the jury, were black. So we're seeing 8% versus 26% of people who could have been called in. So it kind of sounds like they didn't use randomness, right? They didn't randomly select a jury, because you would imagine that it would be closer to 26%. There'd be you would expect to see 26 black jurors on the panel, or potential jurors on the panel, out of the 100 that were there. But we only saw 8, and that seems off. That seems really, really off, and we're going to prove that it was. So the idea is we're going to come up with a model. Our model is well, maybe this was truly randomly. They only picked 8% of on that particular day. They really did just flip a coin to select the jury panel, and it just happened to be that only 8% of the jurors in that panel were black. That can be our model, right? And we can test against that. That's going to be the goal. So that's kind of the question. If that panel was truly selected randomly, it just happened to be that we saw such a small number, we can model that, and we can ask Python to show us how often do we get a number that small when we really are randomly selecting from a population that is 26% black. All right, we can totally simulate that, and that can turn into our model that we can check against. Does that kind of make sense where we're going to go with that? So our model can be the idea that it really was a randomly chosen jury panel from these kinds of proportions, and we can check and see how that model predicts juries. That's going to be what we get out of it. Right, we're gonna tell it to predict some jury populations, please, and that can be our model. So our model is the people on those jury panels were selected at random from the eligible population perfectly. We just saw a small number due to complete randomness, which is possible, right? It is possible, but it seems like it's a really low number, so it seems unlikely. So we can figure that out. So that's our model, and if we see that sometimes it kind of does, it randomly predict such a small proportion, then maybe we can conclude that the county was not systematically excluding people, but if it's hard for our random model to give it that small of a percentage, we can then conclude, right, that there was some sort of bias, and that's called our alternative viewpoint. So our alternative viewpoint could be like, no, the jury was actually biased, and we can look towards that if our model does not predict the data. Does that kind of make sense? That's where we're going, and I want to predict that. Let's make some sample juries now, assuming that we're going to predict, or assuming that our juries are drawn from this kind of percentage, like 26% black, 100 minus 26% white, and we could use that function that we learned about last time. We can use our sample proportions function. Remember that one? So we can give it like, all right, we have, I want to make a jury of size 100, and here are the proportions of the different races that could appear on the jury. Like you have this proportion black, this proportion white, and other races that were in the county, and then we could see like, all right, how many people were actually on that jury of those different races, and we'll see like how often was it so small, right? How often was this number so small? So that's where I want to go. Does that kind of make sense what I want to do? I want to make some random juries, assuming that this model is true, assuming that the people on the panels were selected at random from the eligible juror population. We're going to find that that was not actually probably the case, right? Very, very unlikely. So this is the case of Robert Swain. Okay, so yeah, what we want is, if we want to use this sample proportions function, we need a sample size. I'll make that a variable, and that's just 100, right? We want to make a jury, we want to simulate a juror panel of size 100, and our proportions, what's our eligible population? Here are the different kinds of people who could appear on the jury. We'll just make an array of, all right, it was 26% black, and then whatever 100 minus 26 is for white. 1 minus 0.26. So 74% non-black, let's say. Okay, so that was the population that we could choose from. And do you see how if I call sample proportions right now, it's going to run, and I give it the sample size, and I give it the sample proportions. If I do this, it will generate a jury using these proportions. It won't be exactly, right? It will get out, oh, oops, did I not include something? Sample, oh, I didn't run this up. There we go. Dun, dun, dun. Oh, something else is wrong. Let me figure this out real quick. Must be a string or a real number, not a function. Oh, sorry, this is eligible population. There we go. All right, so this is truly randomly from this from these weights picking a jury, and it shows 27% black people on our simulated jury panel and 73% white people. Does that kind of make sense, or non-black? So that's very similar to our population percentages. It wasn't too far off. If I run this again, I'll get different percentages, and sometimes it's like bigger, sometimes it's smaller, right? It could be way off. This time I got 28% black, 72% non-black on our simulated jury panel. And if I run it enough, we will get some small numbers for the black population. I got 22%, 23%, oh, 33%. 31%, so that's bigger than it should be, bigger than it was in real life. 25, I guess 22 is the smallest I've seen. There's 21, sure. So sometimes it can be a bit smaller just due to randomness, right? But it's still not that far off from the original thing. Does that kind of make sense? And so as I'm simulating these juries, because it was 100 people on the juries, I can multiply what I get back here by 100. I can do my sample size times that. Does that kind of make sense? Because if it's times 100 and these are percentages, that means I got 21% or 21 black jurors and 79 non-black jurors. Does that kind of make sense? How you can, like, there's my simulated jury. That's kind of interesting. We can turn this into a function because I want to predict, right? I want to simulate and see how often, because this is my model now. I'll call this, give me one simulated count of all my jurors, and I'll return this. And you know what? Let me not just return this, let me return item 0. because I just want like the 21. I want to know how many black people were on the jury. I could have also done it in the other way, but we're expecting to see 26. If it's a jury panel of 100 people, we're expecting to see 26 black people if this is if these are the true populations of each race. All right. So here, if I do item 0, I get the first thing. I get the 21. And now I can call this function a bunch of times. Does that kind of make sense what I'm about to do? So one simulated count. And this was, all right, there in my simulated jury, there were 25. All right. 25 black jurors. If I do it again, you have floating point things, but there are 30 of them, right? 30, 25. Oh, that one was 15. So that's, sometimes it does get to be very small. And so, yeah, 22, it happens. All right. So my goal is to see how well this model simulates what happened in real life, because we saw 8% African American jury panelists, right? That is a problem. Let's see how small could this function give me a number back, right? Due to just sheer randomness, if I do like a few thousand simulations, how often do I see a number that small for that proportion? Okay, that's what I want to do. I'm trying to simulate it. We're assuming good faith. We're assuming it was random, and we want to simulate this a few times. And honestly, this could be a question for you guys. Let's make this a crush dice. Here's my question for you guys. Try to create an array called, let's call it counts, because we're doing a bunch of simulated counts. What I want you to do is try to make an array called counts and add 10,000 simulated counts to it. Does that kind of make sense? If you want, you can go to our code from class last time, because we did something similar to that when we were making arrays and things. Like here I was making an array of a bunch of medians. So you might want to look at the chapter 10 stuff for that. That would be useful. But I want you to try this. Try to make an array called counts and take 10,000 simulated counts of the black jurors into there. And we're going to see how often did we see such a small proportion of black jurors. Okay, that is our problem. And we're going to see if our model predicts it, because our model is assuming good faith. And so if we don't see this happening very often or at all, that implies bad faith, right? Implies that there was something wrong, there was bias on this jury. So if it's truly random, we would see it in the output. We would see it in this array, surely by 10,000 times, right? If you have any questions about it, this is a good one to try. Yeah, look to chapter 10 because it's going to be like you're going to do a for loop. You're going to do np.append, right? Appending to the other side of an array. You're building up. You're starting it empty, right? We've seen this pattern before in the last chapter. Try to recreate it by calling. We're going to call one simulated count to have a bunch of those simulated counts of jurors. And I hope you see that our model is really it's trying things randomly. It's really testing things randomly. And so if this jury was really chosen randomly and truthfully without any bias, we would for see that small number that we saw that we thought was wrong. If it truly was possible just to be due to randomness, we would probably see it after 10,000 times, right? At least once. Oops, I didn't see that. Give you another minute to try it. All right, that's my timer. Let me finish this Discord response real quick. All right, that. I hope this made enough sense. So I want to make an empty array, right? I'll make an array called counts, following that pattern from last chapter. And then I want to do this a few thousand times. So I can make a repetitions, did that before, repetitions variable. I want to do this 10,000 times, whatever's in repetition. So you can change this if you want. And then I want to make a loop for I in np.a range just repetitions. What do I want to do? I want to call my one simulated count function to get a new count, a new simulated juror proportion, and I want to add that to my current counts array, that new value, and like that is my counts array now. Make it one bigger, right? Make it one bigger each time. And so if I run it, now I have a size 10,000 array in counts, and those are all the different proportions of, or not proportions, those are actual counts now because we multiplied it by 100, right? This was a jury panel of size 100, and so in the very first simulated jury panel, there were 26 African-American jurors. The next one, there were 23, 27, all the way, there were 22 in the last one. So those are all hovering around the real proportion, right? The real original proportion of the county of 26% eligible jurors, because we were assuming that was like what we're taking things from randomly. We're assuming those numbers were coming from there, and so it's not to say that in the middle we didn't get a number that was like 8. Let's go and check, right? We can check this by seeing the distribution of these numbers. We can make a histogram, right? So let's make a table with these values. It can be like counts in a random sample, and here's counts. So that will give me this giant table, right? So give me this giant table. I can sort. I just say sort on column 0. We'll see the smallest one. It looks like just due to sheer randomness, after 10,000 trials, the smallest proportion of black jurors on this simulated jury, given the 26% population to choose from, was 10. And so it was 1 in 10,000 chance, right, that we saw a size 10 jury in that way. And then sometimes we saw 11, 12 was somewhat there. So like, it's very, very unlikely. This is like 1 in 10,000 times we got that low number. And you see how we never got an 8? We never got the number 8 or smaller. That was so unlikely if it was due to randomness. That's kind of what I'm trying to show you here. All right. So we can turn this into a histogram as well, like I said. So let's take that. Here's this. Let's turn this into a histogram. The default bins are okay, but we can make them fancier. Let's do bins by, just go by ones or something between, I don't know, it looks like we're going between like 10-ish and 40. I don't know, just in case, right? Let's go between like 5 and 45. Bins equals NP to A range. Let's do This is what your book did. Between 5.5 and 46.5. So I guess 6 to 45. Let's do 5 to 45. Why not? Going by ones. It's like 45.6 or something. Going by ones each time. So there's a bin for every one. Do you see? Like we had 10. Like we saw that there was a 10, but there's like you can't even see it here because it was just one thing, right? It was so unlikely. Do you see how usually in our simulation we saw jury panels with about 26, right? With about 26 African American jurors drawn from that population, assuming that's what really happened. If it was due to randomness, the most amount of times you would see that true value, right? You'd see that true value proportionally. Sometimes you'd see more, sometimes you'd see less. It's less and less likely to get bigger numbers as well as smaller numbers. And we didn't actually ever see the number 8, right? You can check that with the sorting. You could also check with, be like, hey, is any value in the counts array ever equal to 8? You'll get back a bunch of trues and falses, right? You can ask, hey, np.non0, was this ever true? np.count non-zero, right? Because if there was ever a true, it would be true is considered 1. And so how many times was counts equal to 8? 0 times, right? You could also ask, like, okay, maybe it was just randomly somehow less than that. Like, okay, how often was it 8 or smaller? That's kind of what we want to ask, right? How often did we see a value that extreme or worse? Out of our 10,000 trials, assuming good faith, assuming no bias, 0 times, 0% chance. Does that kind of make sense? 0 out of 10,000. Did we ever simulate that? Does that make a little bit of sense? Because that's just screaming there was bias. You kind of understand what that's trying to tell us? Because our model, right, was, okay, we are assuming that the county was playing fair, that all the eligible jurors were selected in this way, that we would see 26%, it would be proportional, and we only saw 8 if we just simulated, right? With our one simulated count function, we simulated a jury panel selection of 100 jurors, and we counted how many were African American, and here are all the values that we got back, and it was so unlikely. Out of even 10,000 times, we never saw a jury panel with just 8 black jurors. That's not good, right? So that's telling us that our model, which was like assuming that they were doing it right, our model doesn't really reflect the truth, does it? Our model doesn't really reflect the truth. If we would see the number 8 somewhere if it was somewhat likely, and we didn't. So that leads us to our alternative viewpoint, saying that, okay, there was some sort of bias, and that is unfortunate. All right, so yeah, there was a systematical issue with the way that they were choosing jurors at this point in time in that county, and Robert Swain did not get a proportionate panel of jurors to choose from, and that's unfortunate, I would say. Are there any questions about that? It's a sad story, but we can use math to prove that there was an issue. No, there was totally an issue, and that's not good. So that's nice, though. That's powerful. We can use that in someone's favor. But yeah, it's unfortunate that the Supreme Court ruled differently. I guess their idea was just like the people who get called into jury duty, it doesn't have to be proportionate because of a bunch of different reasons. Like some people have, like they've moved, like their address isn't the same anymore. Like it's not the case that you're going to get the full population and the percentage is perfectly correct every time you try to call people in for jury duty. Some people won't show up, and I don't know. It's not a fun story, and we just proved that there was some bias in this county. Okay, so yeah, that's my first example. I want to do another one about jury panels. Are we ready for that one? It's a little more complicated because I want to talk about not just one. I don't just want to pick out one race anymore. I want to pick out a bunch of different ethnic groups. All right, this was another study that was done more recently, and it was done closer to home. It was done in Alameda County, so like Oakland, and they saw that there was also some issues there. There were some issues with the way that they were picking juries in Alameda County, and it was the ACLU that took them to court. So they saw that some racial and ethnic groups, they found, were being underrepresented among the jury panelists in Alameda County. And so here's the data that they collected and that they complained about, rightfully. So here's a bunch of different ethnicities as defined in like the U.S. Census or something. You've got these different ethnicities that they were keeping track of. And then here was the eligible population for jurors. You would see in Alameda County, like there is 15% Asian or Pacific Islander potential jurors, all the way down to other, something that was not up in any of these other categories. And so those add up to 100. And so that was the population of eligible jurors and the proportions of all of those that could have been chosen from as they were calling people in for jury duty and trying to pick jury panels. And then they took all the cases for a year, and then they did the math and they found that this was the proportion of the jury panels in the end. There was overrepresentation for Asian and Pacific Islander. There was severe underrepresentation again for Black and African American jurors. White, Caucasian was exactly the same, somehow, magically. And again, underrepresentation for Hispanic, not as much as for Black and African American. And other, anything that doesn't fall into those categories, was also a little bit more. So this is, do you see how these were the eligible population proportions? You would expect to see numbers around those for the true jury panels in the end, for that year that they were keeping and tracking the data. But we saw some serious issues where some numbers were more and some numbers were severely less than they should have been. And so that again tries to that makes alarm bells go off in our brain, and we think that there was some bias probably with the way that they were selecting juries again, even in California. So let's figure this out, because again we can make a simulation, right? We don't just need to give to our sample proportions function an array of two things. We can give it an array of any kind of proportion. We can give it the eligible population, and we could ask it, all right, choose randomly some jury panels with these populations, and you show me how often I get this kind of disproportionate numbers for the simulated jury panels. If I use these numbers, how often do I see a simulation that looks like this? Does that kind of make sense? Just like when we were trying to flip coins, we gave it 50-50. We didn't always see exactly 50-50 heads and tails when we did our simulation, because like randomness happens. Sometimes there were more heads and less tails and vice versa. Like we did all this last chapter, right? A bunch of medians, like our sample proportions. Here I was flipping 100 coins with a 50-50 split distribution. We're like, all right, I got 54% heads and 46% tails. Something like that. So I can do that again. I can do that again here for these jury panels, and we can see how often we saw things like this. Okay, so yeah, let's just kind of study this for a second, and we'll go from there. So this is jury selection in Alameda County. I hope that's how you pronounce that, by the way. Oops. I am from Southern California, so I do not know my Northern California county name pronunciations. So, okay. It will be easier for me to copy and paste this table that I like to give you right now. So like this is, here I am making a table for all that data so that we just have it in one place. So here's that. So this is just me taking the stuff from the slide and putting it here. So like here are all the different ethnicities. I made a table with those columns. Here's the proportion of the population eligible to be on a jury, and the splits of all those ethnicities and races. And then here are the true panels that we saw for that year that they were keeping track and like doing the study and doing the lawsuit. And we see the differences, right? Except The only one that was magically the same was Caucasian, interestingly enough. We can do a bar chart, right? Because ethnicity is a categorical variable. So we can do a bar chart, or H, on ethnicity. Ethnicity, if I can spell it. And you can kind of see graphically what the differences was. Like, in order for there to be overrepresentation of some races, then you'd have underrepresentation of others, right? And so that's what we saw, and that's unfortunate, right? So now our goal is, let's simulate some proportions of juries using this eligible population, all right? Let's simulate some proportions of juries and see how often we find something so way off of the original population. All right, that's our question right now. That's again a model that we can simulate with randomness. Like, all right, if we were randomly picking from people with these proportions for those races, how often do we see a result that looks this way off? Okay. So that's, I think I want you to try that. So here, have another crushed dice real quick. So there were, let's see, did I put this here? In the study, I took this from the study, there were 1,453 people on all the jury panels for that year that they were doing the study. People on juries during the study, okay? And I'd like you then to, using the proportions of eligible jurors and the sample proportions function, simulate trying to pick that many jurors. Simulate picking 1,453 jurors. And here are the eligible population counts. Jury dot column eligible. Here are the orders, and it went in this top to bottom order from this graph. So 15% Asian Pacific Islander, 18% Black African American, all the way down the line. So try to do what we just did. Try to formulate a call to sample proportions with these values, with that many people, and try to run it a few times to see how much you get. All right. So try to do that simulation. Does that make sense? Here, if you want, I can give you the code that we've worked on today, just real quick. You want to go to the code from class, you can see everything I've just typed. Now, at least, there's a chapter 11 file up there for you. But try to formulate the correct call to sample proportions, and those are your proportions, right? Those are your proportions. You can keep it in that order because that's the order you don't study. But as long as you remember what was where. But try to call it a few times and see if you saw something that was so way off. How likely is that? Because everything's possible due to randomness, right? It's just a question of how unlikely is it. Because it's totally possible for you to flip 1,000 coins and them to all land on hits. That's totally possible, right? You would just probably be dead if you kept trying, right? It just wouldn't happen in your lifetime. But it's there. It's totally there as a possibility. So yeah, run that a few times if you can. Give you a few extra minutes. Try to, gosh. No, we're not ready for that. So yeah, just try. I'll give you a minute to think about that, and then we'll keep on trucking. All right, let's figure this out. Yeah, let's make the call. Where do I want to be in my notes? I want to be here. So yeah, I want to like essentially these are my proportions. This is my model. This is what the world looked like. Well, that model equals that, and then let's see here. I want to simulate exactly this many people, right? Exactly this many people. So I'll call that. Let me call it something eventually, but I'll just say sample proportions real quick. Sample proportions on 1,453 people, and here's the model I chose, right? And so if I call it, do you see how I'm getting new populations for Asian Pacific Islander, Black African American, Caucasian, Hispanic, and other? They're not exactly the same, but I was choosing this many people from those groups, and just like randomly, as I did it, it got this percentage of those proportions. If I run it again, sometimes we get more and less. Like here, there were fewer Asian and Pacific Islander people on this, proportionally on this jury of this many people, right? So that kind of makes sense what sample proportions is giving me back in this case. Do yell at me if you have any questions, but that is like, that's a simulation, and let's call that something. I'll call that simulated so we can see the difference. I'll call that simulated. I kind of add that to the jury table with a column called simulated. And so I can attach it, like it got eligible, here are the actual panels in real life, and they were far off, and here was the simulated panel of that many jurors, and we'll kind of compare them all. I can call this a new table, jury with simulated. Jury with simulated, and we can do a bar chart of that. Ethnicity. And so do you see, you got the eligible panel population, you got the real panels in real life in yellow, see how far off they were from the eligible population, and then we have our simulated panel. Our simulated panel of that same amount of people, do you see how, these are the light blue bars, do you see how versus the original dark blue bars, they are very, very close. They're not perfect, because it was randomly chosen from those populations, but if it was randomly chosen, right, from the population, you can see like it's not ever going to be that far off usually, right? If you're doing it completely randomly, if that's the true way that things were being chosen, these populations were being chosen, right? We want to see like, did that really happen? It is possible if I run sample proportions again and get a new amount of simulated things, do it again, they went a little bit off, right? A little bit more, a little bit less in some areas. But do you see how the dark blue and the light blue lines are pretty much in lockstep? Usually, if that was the only way that they were picking juries, you would see that, right? Usually that would be the problem in the case. So, yeah, just goes to show there's probably something wrong with these panels. We want to see how unlikely this all was. All right, so our question is, now that we can make simulations, if we can make some simulated panels and get some proportions, our question is, like, we want to know how far off we were, right? How far away we were from the true values to see, like, to get a number, right? We can't get our number by just like subtracting things, right? Because before, like the things that we were simulating, right? We were simulating how many specifically African American jurors were there on this simulated jury. We can't get just one number anymore. We have this giant eligible thing, right? We have a bunch of different proportions for a bunch of different ethnicities. We want to compare them kind of all at once and get some distance away. Like, how far away are all of these at once from each other, kind of. So I want some sort of number like we were doing last time, and it's a little bit harder to get, right? We just can't we can't subtract and see how far off we were because we have a bunch of different populations, right? We have a bunch of different people and ethnicities and things. So that's our next question. We need some new way of doing this kind of comparison. Okay, so yeah, let's just for posterity, let's write that down. So there aren't just two things to compare now. It's not just like black versus non-black. We have a bunch of different ethnicities and their proportions, right? That could be off, could be right. Our goal, kind of like we were doing last time, so we can simulate in an easy way, our goal is to make just one number to represent the differences in all of these ethnicities at once. I want to represent all the differences in these distributions, like how far off is Asian and Pacific Islander, as well as Black African American, as well as Caucasian, as well as Hispanic, as well as other, all at once. Give me one number that describes how far off this distribution is from this original one. Yeah, that's what we want. We need some new statistic now. We need a new statistic to measure the difference between the distributions. All right? That's what we want. All right? That's what we want. We want to measure those differences, and the way that you do it, the way that we're going to do it is called the total variation difference. All right? This is where we're going, and this will be the last thing. We'll do some simulations. It'll make it all work. So what we want to do is we want to see whether like how far off is this distribution of ethnicities from the original one? How far off are they all at once? Give me one number that represents how far away they all are from each other. That's kind of called a distance metric, right? The word that we're looking for is distance. How close are they? How far away are they? So we want to measure the distance between these two distributions of categorical ideas, right? These guys in that order versus these guys in that order. How far away are they all together in one number? And so one of the ways that statisticians do this kind of difference calculation is called total variation difference, or total variation distance, or TVD for short. And what we're going to do is, for every one of the categories, we're going to subtract. We're going to get the difference between these guys and these guys and these guys and these guys. We'll come up with a bunch of differences. How far away are they all? And then we're going to take the absolute value to measure like how far away were each of these. It didn't matter in which direction. And then we're going to sum them all up. And we're eventually going to divide by 2 for an interesting reason. We'll talk about that. And that's going to be our one number that's going to represent how far away those two distributions were. And then we can compare against that. All right, that is our goal. That's where we're going. And yeah, let me try to show that to you. So here, we want to calculate the differences. So we've got this jury table. We've got jury.column. We've got the panels column. And then we've got the eligible column. We want to subtract the two. Jury.column eligible. All right, and I want to subtract the two. And these are like the differences between what were actually on the panels versus the people who are eligible. Like we saw so many more Asian Pacific Islanders, so many less, 10% less, right? Black and African American jurors. And this is like all those differences at once. And so let's make a table with all those in it. We'll call it jury with difference. It's jury with column difference. Sorry, I got to finish off that first line. Eligible. We got all those things. And show me that. Oh, sorry, I want to call those differences diffs. And so what I've done is I've taken panels and I've subtracted eligible from it. Like how far off are all these things? It was 11% off for this one, right? To go from here to here. It was negative 10% off to go from here to here. Like that was the difference between each of those individually. I want to bring them together, right? I want one number that describes all these differences. And so one way to do it is to just like count how far away is everything. You can do absolute value. You can do other things. But first of all, I want you to notice something interesting. This is true of any kind of difference in proportions. However much you go in one direction, you must also go in the other direction for the other people. So do you see how there was a big increase for Asian Pacific Islander, 11%, as well as a decent increase for the other population. It was 14% pushed in the bigger direction. I guess that's that way for you. You also see that push in the opposite. What goes up must come down somewhere else. So do you see how there's negative 10% as well as negative 14%? That's negative 14% in the other direction, right? Positive 14 in one direction, that means something else got pulled. The other things got pulled negative 14 in the other direction, right? That's true for everybody. What goes up must come down somewhere else. And so to get a number out of like how far away are these, we could just like count the positives or count the negatives. So they're both 14% off, right? So that's kind of interesting. So what I'm trying to say there is like, here's my jury with difference, and we can go where the difference values are above 0. Those are all the positive differences. And then go to the difference column. And I can sum them all up. It's 14% positive differences. And it's same for negative. It's interesting. One tuf must come down as negative 14 for the other two. That was doing something like that. And so one way to calculate this, like this could be our number. That's what total variation difference is. Like that could be our number. Like how far off was everything? That's our total variation distance. One other way to get it is to take the difference column. You can see that if you summed them all up, you get 0. So a number that's very close to 0. You could do a sum of the absolute values. So take the absolute values of the differences. So here's the difference column. We could take the absolute values of everything. Abs is the function that does that. So now they're all positive, and then if you sum those up, we're going to get 28%. That's all the positive, like everything, all the negatives became positive, and so now it's, if there was 14 in one direction, 14 in the other direction, now it's 28% total. If we just want like one of the sides, like how far was one pushed one way, one pushed the other way, because it's always half and half, you can just divide that by 2. So that's kind of the quicker way to calculate total variation distance, right? Total variation distance. So you take these differences, and then you see like how far was one being pulled one way and one being pulled the other way, because it will always be equal. And one way to calculate that is take the absolute values of all these differences and divide by 2. All right, because the negatives will match the positives, and that's not telling you anything extra. All right, but that's one way that we came up with some number to represent the difference between those populations. So that kind of makes sense. We just need some number, because now we can compare against that one special number. Yeah, that's what we want. So the total variation distance between what we saw in real life, the panels of jurors, and what the population looked like was 0.14. That was our number. That was our distance number. Okay, that's what we got. And so, yeah, we can calculate total variation distance on a bunch of different values. We can make a function for that. Like def TVD. You give me distances 1, you give me, you give me distribution 1, you give me distribution 2. I'll give you back the total variation distance between those two distributions by taking dist 1, subtracting dist 2 from it. It doesn't matter because you're going to do absolute value. Take the absolute value over all of those, sum it up, and divide by 2, because the positives and the negatives, they kind of cancel out. I'm sorry, I need to return that value. And so now what I can do is I can say, how did I get these values? I can say, it was the panels and the eligible columns, wasn't it? I can feed those into TVD now. Like, all right, TVD on the panels column and the eligible column, how far away were those distributions from each other? What was their total variation distance? 0.14. Yeah. Any questions about this function? We're just trying to get a number that represents the difference between those two proportions, those populations. Give me one number so that I can compare against that one number. Yeah. And the question is now, if I do some simulated juries, what is the total variation of those simulated juries versus the original eligible population? Yeah. So if I do another simulation, if I do sample proportions on my model, all right, there's some proportions. How far away were those from the eligible population? Boop. Call TVD on that. This is me coming up on the fly with a new unmatched. Oh, there. So here it is. It's coming up with a random population, or a random picking of juries according to our eligible population model, and then subtracting that from like the distribution of the original eligible population. It is so much smaller than 0.14. So it kind of makes sense. So if it was truly due to randomness, those differences in the juries, how likely would it be that we saw a difference, a total variation difference between those distributions of 0.14? Because it looks like every time I'm trying to create, due to randomness, due to my model, a new jury makeup, then I'm not seeing anything really bigger than like the 0.35. And that's the biggest one I've gotten so far. Does that kind of make sense? Because they're usually going to be pretty close. So I want to simulate this. I want to simulate this now. All right, so I want to make a simulated total variation difference. This is me doing that, right? And we can call this, by the way, this original value, this 0.14. This is our observed value, what we saw in the wild. Observed total variation distance. And print it back out again. And this one, it's always changing, right? This one's always changing because it's a simulated thing. So let's do a bunch of simulations again. Let's do that. Right? I'll make a function called simulated total variation distance. I want to return this. So this is me making a random jury with exactly how many people were on there in the study with the exact proportions of the ethnicities from the study. And I would like to call that a bunch of times and see how often do I get a TVD this large like we saw in real life. Because if I didn't see that very often, that means that there was some bias again, right? The TVDs equals make an array. And now I want to try this a few thousand times again. All right, so this might be something for you to try. So yeah, let's get some practice because we're just gonna keep doing this, right? Here's my question for you to try. Just try to simulate 10,000 total variation distances into this empty TVDs array. Can you do it? Give you a couple minutes to try. And if you finish early, try to see like how often did we see a TVD value of 0.14? How often did we see such a large distance between what it should have been, right, the makeup of the true populations of the different ethnicities in the Alameda County versus what was in. Because our simulation, our model is assuming, right? Our model is assuming that they're just randomly picking people fairly from all those populations. That's what we wanted. Try to do that. If you've lost the, what's it called? Let me give you all the code real quick if you want to refresh the page. There, now you've got everything. If you want to scroll up to get the actual proportions if you don't have those yet. That should do it. You finish early, try to do a histogram. So that's what I'm going to do. Try to see how often we saw a proportion that was so large. Let me know if you have questions. I'll be here. So that's, now you kind of see what I meant by model. This is like, all right, due to randomness, we're going to assume that this is the way that they're really picking things. So that's what we hoped for. And if our model doesn't match what we saw in the real world, then they must have not been actually picking people randomly, right? And that gives us some good knowledge. It means we can go sue some people. All right, let's take a look. So I can do kind of the same thing we're doing up here. We did 10,000 up here too, didn't we? Why not? For fun, you don't have to, you can hard code the number of repetitions. You don't have to say the word repetitions if you don't want to. Call it gnome simulations if you want to, as long as you're consistent. Put it there. But what I want to do is not called counts anymore. Let's get rid of all that. I would like to get a new total variation distance by simulating it. So I'll call it like new TVD. Give me that simulated one. All right. And then I can add that to TVD's array. TVD's dot, np.append to TVD's, that new TVD, that new total variation distance for the simulated jury panel. Set that back into TVD's. And it'll run. It's pretty fast. And then I have a size, legitimately 10,000 array of all these different total variation distances for all these jury panels. And the question is like, all right, if it was due to randomness, sometimes it's never zero, right? Zero means they were exactly the same distribution. It's not always the same. It's a little bit off in different directions, and the absolute value makes it always positive. Like, so 0.2 is the largest thing that I see here, but maybe in the middle there's something larger. Our question is, how often do we see a value of 0.14? Because that's what happened in real life, right? That's what happened on the actual jury panels. How often did we see that versus that? Because that was a huge, stark difference. That's why we started thinking about this. Was that really due to randomness? If it was, we would have seen something that far away in our simulation, right? That's the goal. If it really was that this was possible due to randomness in our lifetimes, then 10,000 trials, 10,000 making up juries, we should see some 0.14 there, right? Let's figure that out. So it can be like a table with a column. We've got, here, I'm going to do something real fancy. I'm going to make a fancy thing. You don't have to worry about it too much, but remember how you could make a, like you could change the x limits and the y limits of graphs. Like I want to do that here, just to make something fancy. So I'll say the title of this graph is going to be simulated TVDs. And this is all under the assumption if the model is true. If the model is true and they were legitimately picking jury panels from the eligible population properly, perfectly randomly. So there's that. I want to use these bins. This is a good one. 0 to 0.5, 5 with that far off in between, and I want to call this, use the title, use the TBDs, and then I want to make a histogram with those exact bins. And so that's a little bit weird, but let me keep typing. You don't have to worry about what I'm trying to do here. I also want to plot our 0.14, right? Because I hope you can see there's no 0.14 on this graph. So I want to plot the observed TBD. You don't have to worry about this code. I will not test you on it. Ignore this code. I'm just going to put a red dot where what we found was. So it's like plot dot while limit -2 to 55. Plot dot scatter observed TBD 0 color equals res. Just a bunch of library stuff. You don't have to worry about. Size equals 30, and then semicolon. So I don't see the output here. That should be, oh, sorry, I want 0.05. There we go. There's my graph. This is the distribution of our simulated jury panels and how far away they were from the true population. 0 would have been our true population. It looks like they're not always perfect, right? It's not always on the money. They're always a little bit farther away, just due to randomness, about 0.2 total variation distance away. Sorry, 0.02 total variation distance away are simulated panels. At most, they seem to be about 0.05, right? In our simulation, we simulated 10,000 juries of those sizes, which is just impossible for them to have ever done. Like, they won't make that many juries in several decades, I'm sure. So we are definitely doing more than they could ever do. And here, that red dot right there, that 0.14, that is what we saw in real life. Do you see how not predicted by our model that number was? Do you see how far off that was? How that was just not a value that could have been due to randomness. Then it was so far away, right? You can ask the question like, all right, how many times in my TBDs simulated things was it equal to 0.14, or even bigger? You can say np.count non-zero. Like, how many times do I see true for this? The answer is 0 out of 10,000, right? And that's kind of a percentage. Like, all right, if this were to ever happen, how often would it happen? 0 out of 10,000 times 0%, right? So that, again, gives us reason to conclude that maybe the alternative viewpoint is true and that our model does not actually reflect the world, sadly. They weren't actually drawing from the eligible population properly, or there's always some systemic issues as well in the way that you call people to jury duty. Like, you can imagine that jury duty requires people to have a fixed address, to be not moving around too much, to have transportation to get to jury duty, to be able to easily get off of work without any repercussions, even though you're supposed to legally be allowed to go to jury duty. Like, there's a lot of people in situations where they just can't get to jury duty even if they're called, right? And that can affect disproportionately different races. It's very unfortunate. So that goes to show, like, if they really were drawn randomly and the juries were proportionate to like the way the county looks, they would have been over here, but we saw something way over here, which means the juries were not proportionate. They were biased. It is hard to fix that bias, but without a doubt, they were for sure biased. There's a 0% chance that you saw something that far away due to randomness. Does that make sense? So that is not a fun story to tell today. A couple of sad stories. It's unfortunate. There's systemic issues in the way our country works, and it's just not, it's true everywhere. But maybe if you become a lawmaker, you will use these powers for good. Now you know how to check this stuff, right? Because that was the goal of this chapter, right? That is the goal of this chapter. We have some hypotheses like, hey, are these juries being made in a fair way, in a proportionate way? And we're able to answer those questions, right? We're able to answer them is by saying no, but we're still able to answer them, all right? And so that it's an interesting idea, and I hope you see its power. And I think that's where I want to stop for the day. Are there any questions about any of that? All right, so let's see. Let me mark where we were with my favorite blue-colored slide. I'll say to be continued. And then I think that'll be all. So to be continued. I will give you all these things that we talked about today and all the code that we wrote. Good to study. And yeah, I think that's all that I wanted to say. I don't think I have anything new to release to you. I do want to talk about what's called the mid-semester anonymous feedback survey, but we can deal with that on Wednesday. Because we're in about the middle of the semester. I like to give out a little survey for you guys to like evaluate the class in a way that I could see, and that's anonymous. But we can talk about that on Wednesday, I think. So yeah, just make sure to do attendance if you haven't already. I'll keep that open for a little bit because I forgot to stop it. And yeah, the rest of the time is all yours to work and ask questions, and I will work on giving you all the stuff we did.